our lecture today. So we're going to finish off chapter 2, fluid statics, with that last topic, rigid body motion. And then we'll move on to fluid dynamics in chapter 3. So this textbook starts off by introducing some simple fluid dynamics analysis. And in particular, we're going to develop the equations describing the motion of fluid, starting off with our Newton's second law, but in a special manner, in an ideal manner to simplify the math and the analysis. And so this is referred to as the equations of motion, or F equal MA, in streamline coordinates. And so I'm going to define what that is. And so we're going to develop the equation along streamline and then in the normal direction. And then using this equation here will allow us to develop the so-called Bernoulli equation. And then we can do some very simple basic analysis of fluid dynamics using that. Okay, so I'm not sure how far we'll go today, but at least I hope to consider F equal MA along the streamline coordinate. Now, the one other thing that I want to address is I apologize for the TA having to cancel his session today. And for now, the TA had a family emergency that he has to handle. And so for now, I asked my other graduate student, Scott Carlson, to step in as TA. And many of you know him because he was the TA for MAE 11. And and he's TA'd 101A before, and he is scheduled to TA 101B. But for the time being, he'll handle homework solutions and grading of exams, those sorts of things, homework submissions. And for now, I'm thinking that I will do the discussion session. So tomorrow I have office hours, Thursdays at 11 a.m. And I'm thinking that I'll make that a discussion session. In fact, I could make the Tuesday office hours really a discussion session as well, since it has been sort of a small group discussion. And I think that then if you have specific questions, you can certainly ask me after class, and I can stay, after for some time and address any individual questions. And so we could see how that goes. And if needed, I could provide additional time as office hours, and just see if that meets your needs. So I would be available 5 days a week. If you have any questions, we can do discussion sessions, and I can review the lecture topics that we've discussed. I can address any questions on the homework, go over some sample problems, anything that you need. So we can discuss this again on Friday when we're together in person. But I'll post an announcement or revise the syllabus so that you have Scott's name and email. And then regarding my office hours being changed to session. Okay, any questions? All right.
I have a question, Professor.
Yes, go ahead.
Are we going to go any other sections in chapter 3 besides that's after 3.2?
Chapter 3. Oh, the new chapter.
Mm-hmm.
Well, I haven't started discussing it yet. Are you referring to my title slide here?
Yes.
So this is, yeah, this is the title page for the slides that I posted for the notes. And
Mhm.
Bernoulli equation is essentially a form of conservation momentum, but to do flow analysis, we also need to bring in conservation of mass. So that's not really formally done in the textbook. So I want to discuss that. Then we'll go over applications. And then homework 3, I'll post homework problems from chapter 3. I don't have the text sections in front of me, but I think we will probably go over most of chapter 3. Was that
Okay,
your
thank you.
question? Yeah, and then what I did was this is just mainly I wanted to just say what we're going to go over today and kind of where we're heading with this. Okay?
Yes, thank you.
Okay. All right. So now I only brought in several slides from the previous lecture only to recall the general equation for the pressure distribution to start the rigid body motion. So it's just, what did we do back then at the beginning? And just to recall, so I'm only going to spend less than a minute on this. So remember, chapter 2, fluid statics, the primary case that we considered is when we consider fluid at rest. So of course, fluid statics, that's fluid at rest when there is no motion of the fluid, and then we can consider hydrostatics and in particular pressure distribution in a fluid at rest. But when we developed the equations for the pressure distribution, we kept the acceleration term in so that it allows us to consider rigid body motion when the fluid does move, but it does so as a rigid body. That is, there's no relative motion between fluid particles. So for example, if you have a tank of gas and you consider the whole thing accelerating all together, so each fluid particle experiences the same acceleration, and this body of fluid will move as a whole. Okay. Also, it'll just the whole thing will translate. We can also one can consider the rotation of fluid, and in that case, there would also be a rigid body motion. That is no relative motion. And if you have no relative motion, you have no shear. And so when we develop the equations, recall that F equal MA applied, the net forces that we considered are body forces and forces associated with the pressure. So that's the case. And when we applied Newton's second law, we kept in the mass times acceleration term to allow for us to consider this rigid body motion. Okay. So then, if you recall, we obtained this equation, which has that acceleration term, just solving for the grad P. It's a differential equation for the spatial variation of pressure due to gravity and any acceleration that may have the body fluid undergoing. But then we just said, okay, we're just dealing with hydrostatics, so acceleration is 0. And this was our general equation for the hydrostatic pressure distribution. But we're going to go back to this and put this acceleration back in and consider this as the general equation for the pressure distribution. And so it's a differential equation. And if one solves for this, one can obtain in general the pressure as a function of space. Okay, so let's just go back to this, and we're not going to spend too much time on it, but it's a nice it also introduces some basic concepts for this equation. The pressure gradient is a vector. So again, it's a vector equation. And one notices that the pressure gradient, so we call grad P, which is partial P, partial XI in the X direction, variation of pressure in the Y direction, variation of pressure in the Z direction. So again, if we take Cartesian coordinates, what this equation tells us is that the direction of the variation of pressure in general is going to be G minus A. So it acts in the direction of the G vector minus A vector. Okay, so let's just look, for example, in the XZ direction, a 2D problem. And so if we have just the pressure due to gravity, our hydrostatics equation, then grad P equal rho G. Okay, so the pressure varied in the direction of G, okay, and increasing in the direction of G. So the gradient of pressure, that vector, okay, was in the same direction as the G vector, okay? And then you see the line of constant pressure, lines of constant pressure or surfaces of constant pressure are perpendicular to the gradient vector, okay? But now if we introduce an acceleration, so let's say we have this, maybe it's a tank of fluid, H2O, and we introduce some acceleration. So let's say the acceleration is in the X direction, okay? And then we still have gravity in the minus Z direction. And so this equation here immediately tells us that the pressure gradient vector is G minus A, or in this direction, that would be grad P. Okay, so if you have a fluid acting under gravity and an acceleration, okay, then your pressure and the fluid itself is going to look like this. So for example, if this was an open tank, okay, and then here's the free surface, and there's atmospheric pressure. So we consider at the free surface, the pressure is the P equal P naught, right, at the free surface. But now, if we have this acceleration, okay, then the pressure is going to vary in this direction. So the free surface, which is a surface of constant pressure, is now going to be in this direction, okay? And lines of, or surfaces of constant pressure are going to be along lines like that. Perpendicular then to those lines of constant pressure is the direction that the pressure varies, okay? So that's the significance of this. And then to do an analysis, let's see, for example, there's the classic example of if you have some quantity of fluid and say it's a liquid and it's undergoing free fall. So this is an example. So in free fall, the acceleration is equal to gravity, so that you can see that if that's the case, okay, then the right-hand side is 0. And so if this object is in free fall, acceleration, and then we have gravity, then there will be no, according to our equation here, there will be no variation of pressure within the liquid or the fluid, okay? Now, a more interesting example. So suppose we have some, again, let's just consider this tank of fluid here, really the previous example. And let's say we have this tank of water. Let's say it's like an aquarium. It's the classic problem of considering an aquarium. And let's say you want to transport it in your car or truck. And so as you drive, you're going to be undergoing acceleration. So let's consider the case where we have an acceleration in the positive x direction, in the direction of motion. And of course, we are still going to consider that we have gravity acting downwards. And so the problem, let me just redraw this in 2D, is going to be, so given the dimensions of your tank, if you're going to undergo acceleration, then we have this idea that the water level, the free surface, is going to orient in that like this. And if the acceleration is sufficiently large, then we expect the liquid to spill out if this free surface exceeds the side of the tank. Okay, so we might consider this practical question. So if this distance is d, the depth that you fill the tank, and you have dimensions, let's say here we have the length of the tank, L, and then in this direction, the width of the tank, and maybe the overall height. Okay. Then suppose, we may have some idea of our maximum acceleration. Then how deep can we fill the tank with water without it spilling out for that max acceleration value? Okay. All right. So let's consider now the problem. So let me draw here with what we can do, black. So let's consider the let's do this in XY. I think that's what I had in the notes. So let's just consider the 2D problem. Y is vertical and X is horizontal, and then in the we'll be considering acceleration in the X direction, and then the gravity vector is going to be minus G being the magnitude, and it's going to be in the Y direction, the negative Y direction. So minus J, the unit vector in the Y direction. Okay, so now we apply our basic equation. So basic equation is grad P is equal to rho G minus A. And for this particular problem, let's see. So let's do this. A is equal to AXI. So we formally have our acceleration vector and our gravity vector. And in general, we have the pressure gradient here, okay? And for the 2D problem in XY, we would then just have the first two terms, okay? So then we have also, well, so we consider the components. So in the X direction, we have our partial P, partial X, okay? And on the right-hand side, because we only have the acceleration in the x direction, since gravity is in the y direction, then we're only going to have rho, and there's the negative sign here, minus rho ax. Okay. Then in the y direction, we're going to have partial p partial y. And then we'll have our gravity, which is in the minus y direction. So we're going to write minus rho g. Okay, so those are the two component equations. And then in general, we can consider p as a function of x and y. And we can also consider the change in pressure, dp, a small change in pressure between 2 points that vary, it's from x to x plus dx and y to y plus dy, okay? Between those 2 points, the variation or change in pressure can be expressed as dp equal partial p partial x dx plus partial p partial y dy, okay? And then we can apply this to this problem. And in particular, if we consider at the free surface, okay, when we have our body of fluid with both the gravity and the acceleration imposed, okay, then the free surface is going to be this, okay? And along the free surface, okay, we can apply this equation at the free surface. And along the free surface, as I mentioned earlier, the pressure is going to be constant. So at the free surface, dp is equal to 0, okay, is equal to, now we can replace the components with what we've got here. So partial p partial x is minus rho ax, and then we have dx, plus partial p partial y is here, minus rho g, and then we have dy, okay? Now, then we can solve for, actually, dy over dx, which would give us the slope of that line, that free surface. So solving for that, we get dy dx is equal to, and it looks like a minus ax, the density cancels, minus ax over g. Okay? And from our geometry here, we have, so from our geometry, we can replace the slope here. So let's see. If we consider, so let's see, what did I do in the notes? Okay, I'm not going to use h. Let me use e as this height here. Okay, and by doing that, if we consider this angle theta, okay, then we can express e as being, so this distance here is L over 2. So L over 2 tan theta is going to be L over 2 minus dy dx, so minus slope, is equal to L over 2, and substituting in for this, we have ax over g. And then, let's see, so we have E, we can express in terms of what we're after, the depth. So E would be, let's see, did I, a little bit imprecise of E. E is the distance here. from the tank height down to the original surface here. Okay, so then we can express E as H, the height of the tank, minus the depth of the fluid. Okay, so let's see, E is equal to, so let me shrink this down. So we can replace E with H minus D equal L over 2AX over G. And then solving for D, so we have like a D max would equal, let's see, so the D max would, okay, let me see here. Okay, so we have, okay. Oops, well, this doesn't matter, but this is E and this is our theta. Okay, so now we substitute in for E and solve for D max, which would then be H minus L over 2 AX over G. So now, it's sort of a simple point or calculation to evaluate sort of the maximum that you can fill the tank before it may spill over if you drive at some particular acceleration, AX. Okay. It also allows you to, let's see. Oh, maybe we can see that right here. E is equal to, okay, so what you want to do is minimize this distance or the orientation of this. And it also, from this equation, you can kind of tell which way you might want to orient your tank. So if you have the width of the tank, W, and then the long length, L, okay? And if this is the simple equation to evaluate this distance here, you'd want to, for a given acceleration in gravity, minimize, as it turns out, this dimension, okay? So in order to do that, you'd want to orient this side along the direction of acceleration, and you get a smaller E. So this is the sort of thing that one can do with assuming rigid body motion and using this, our general equation, and leaving the acceleration term in, okay? So I did assign a homework problem that I think, as I recall, is very similar to this tank problem. Okay, so that's the last topic in chapter 2. So now let's move on to chapter 3. So we're now going to consider the fluid dynamics in a simplified manner. Fluid dynamics. Okay, so so we just went over the fact that what we've based our analysis on is the governing equation, F equal MA, Newton's second law. Okay, and although we did leave acceleration in, that was for the special case of the fluid moving, the whole body of fluid moving as a whole. But now we're going to consider fluid motion a little more in general. Okay, and the governing equation is still Newton's second law, which is a statement of conservation of momentum. And we're going to develop an equation in general. The equation of motion will be developed in a similar way as this, okay, and in a general manner in chapter 6, okay? But we're still going to make some simplifying assumptions in chapter 3. But the basic analysis is actually similar to what we did previously for fluid statics. We're going to consider a fluid element, okay, an incremental fluid element, and then consider, in general, some coordinate system, and apply Newton's second law to describe the motion of this fluid element, which then, in general, may, now vary in 3D space and time. And not only is the pressure going to vary, but we'll have the velocity of the fluid varying in space and time. And so when we apply Newton's second law, we have to consider the forces. And again, the forces will be both body forces and surface forces. And we'll again consider body force due to gravity and surface forces due to pressure. Now, the simplifying assumption that we'll still maintain is no shear stresses, okay? So in general, surface forces, there's both pressure and shear, or normal and tangential forces acting on the areas, surfaces of our fluid element. But chapter 3, we're going to assume no shear stresses. And remember, when we discussed the shear stresses in chapter 1, okay, the shearing was due to relative motion and viscosity. And a way to neglect shear stresses, viscous shear stresses, is to neglect the viscosity. So let's see, is there a question here? What does E stand for? Okay, so I think I explained that better in the diagram. Okay, so so we're going to sort of follow a similar sort of or a comparable sort of analysis to get our governing equations. Okay, but let's just continue here. So so in general, for our fluid statics, there's no motion of the fluid. We apply F equal MA, and ultimately we get a differential equation for pressure distribution. Okay? In fluid dynamics, now we have to bring in the velocity. Okay, so if we consider in general 3D space, so X, Y, Z, and we have our fluid motion, okay, and the lines sort of indicating the direction of the flow. I'm going to be more precisely define this in a second. But let's consider some fluid particle, and at this instant in time, and at this point in space, it's going to have some velocity v. And velocity in general is a vector, and it may vary in 3D space and also in time. We may have an unsteady flow. And in general, the velocity vector may have the three components. The component in the X direction, component in the Y, and a component in Z. And each of those components may be a function of space and time. So there's the X component U, the Y component V, okay, and the Z component W. Okay, so the X, Y, Z components of the velocity vector. And we'll also have in general then the pressure, which may also be a function of both space and time. Okay, and in general then the governing equations, okay, in addition to our F equal ma, so the same basic governing equation, conservation momentum. As I mentioned, we also need conservation of mass. And so in principle then, we have two equations and then two unknowns for the case where we assume density is constant, okay? Which we had done for the case of fluid statics, for one of the cases. Now, you can kind of see that things are going to be a lot more challenging. This acceleration we write as dv dt, okay? But this derivative here, dv dt, in general, may be more involved, because if you think about it, the velocity is a function of both space and time. Okay, so one is, has to account for that when you take this derivative. So things can get very complicated, and we're going to consider the general case in general, in chapter 6. Okay, and we'll derive and develop the full equations of motion that describe the velocity and pressure in space and time. It'll be a set of differential equations that can be solved to determine both this and this. But in this textbook, first what is done is we're going to consider a simpler case. Okay, so as I mentioned, okay, so first of all, the first thing that we're going to do is, in general, although you can consider three-dimensional space as described by Cartesian coordinates or cylindrical coordinates, depending on the geometry of the flow problem, what may simplify things, the analysis, is if you consider streamline coordinates. So that's what we're going to do in this chapter. And what is a streamline? So a streamline, so if we, I just sort of drew these lines here. And if we have, let's just consider first a steady flow, okay? And so imagine a flow that may change in space, but doesn't change in time. And a streamline is defined as a line everywhere tangent to the local velocity vector. So if I look at this point here, okay, then the velocity may be in that direction, and you can see then the local streamline here is tangent to the velocity. At this location, the velocity is in this direction because the streamline is tangent to that direction, and so forth. So if you look at streamlines, then it'll show you it'll indicate the direction of the velocity or the flow at any point in space. So you can kind of see how things the general motion of the fluid. So as an example, if you have, say, a flow passageway that may decrease in the cross-sectional area, like a nozzle, then if I indicate the streamlines, maybe the center line streamline might be straight through, but near the wall, the streamlines will have to curve. So the streamlines and the flow has to follow the geometry. Okay, so then if you just look at the streamlines, then you have an idea of the direction of the flow. And specifically, it's always tangent to the local velocity vector. Now, we're going to develop the equations of motion in streamline coordinates. And so if you consider now a particle, a fluid particle, okay? So we're going to choose the coordinates at that location. The streamline coordinate, for which this S hat indicates the unit vector in that direction, is going to be in the direction of the streamline at any location. Okay, so to describe the motion of the fluid particle, by definition, the motion of the fluid particle is always going to be in the direction of the streamline by definition. And then the velocity, okay, is only going to have a component in the S direction. That is, V is going to be Vs in the streamline direction. Okay, so basically the speed of the velocity is all going to be in this direction. So that significantly simplifies things. Now, if we just envision a 2D flow, then we'll also have to consider the normal direction. So let's call this N hat. Okay. And so actually I didn't draw it in this, I didn't draw it accurately. The way that I drew the streamline here, the curvature is such that the radius of curvature is maybe somewhere here. Okay, so if I indicate the radius of curvature and denote it as R, then there's going to be the corresponding direction towards the center of curvature, and that's going to be the normal coordinate, N. And in general, then, we can describe the fluid motion using streamline coordinates S and N along the flow S and normal to the flow N. Now, this fluid particle is going to be always moving along the streamline. Okay, so the distance along the streamline we denote as by S. So S is equal to the distance along streamline. Okay, and then this guy, or the velocity, the speed of the particle V, is then just simply ds dt. Okay, the rate of change of the of S, or the coordinate of that fluid particle. Okay, and then the radius of curvature, you can see, is also going to be a function of the streamline coordinates. It's going to change, and basically we can use N. So if we follow S, okay, that's going to be the direction or the coordinate along which the speed changes. And then the normal direction will account for changes in the direction of the flow. Okay, so then ultimately we're going to apply Newton's second law. So we're going to have to consider the acceleration vector. Okay, so in streamline coordinates, okay, the beauty is we only have the speed in the S direction, it's never in the normal by definition of the streamline coordinate. Okay, and then in general, the velocity is also going to only be a function of S, but also that can change in time. Then, if you want to determine the acceleration, so the acceleration vector in general is going to have a component in the S direction and a component in the normal direction. And AS is going to be, well, so we have dVs dt, okay, which is dV dt. Okay, and knowing that the velocity in general is a function of S and T, we can use chain rule. So the rate of change of the velocity with respect to time, plus how the velocity changes along the coordinate direction, S, and then how S changes with respect to time to account for the functional dependence of both S and T. And then this guy here is just the velocity V. So in general, our acceleration in the S direction can be written as partial V, partial T, plus V, which is ds dt, partial V, partial S. In general, to account for the change in the magnitude or the speed of the velocity of the fluid in time and along the coordinate S. And then the normal component is going to be the centrifugal acceleration. So this normal, the normal acceleration is V squared over R. So from basic physics, if you recall, you can express or evaluate the centrifugal acceleration as V squared over R. Okay, and that is in the direction of the local normal vector. Okay, so I think this just sets up everything. And then tomorrow we will, no, Friday, I'll go ahead and what we're going to do is go back to, well, what we're going to do is now that we've defined the velocity and how that's just an acceleration and how that's described in the streamline coordinates, which is what I explained here, we'll then consider a fluid element and then apply the F equal MA in both the S direction and the N direction, considering both body forces and surface forces due to pressure. And then we'll get our equations of motion in the S and N direction. And that's sort of the first objective, okay? Okay, thanks for joining me in a Zoom lecture, and we'll see you all Friday. Keep your eyes open for announcements. Tomorrow, my office hours will be a discussion session.
I have a question, Professor.
Yes.
So on Canvas, it says that, well, for the TA, his office out, there's a discussion section at 12, but in the message, he said it was office hours. So is this meeting at 12 on Wednesday actually office hours?
I'm sorry. So, okay. So as I discussed at the beginning, the TA right now is not available to work as a TA. So for the time being, to address, so he has canceled all the TA sessions.
Oh, okay.
The TA office hours and the TA discussion sessions. And for now, I will provide discussion sessions. So I thought tomorrow, rather than office hours, I will give a discussion session, and maybe Tuesdays as well. And office hours, I can handle any individual questions after class, Monday, Wednesday, Fridays, any class, I can stay after. And then we'll see how it goes. And if I need to, if additional needs arise, like if I need to maybe schedule additional office hours, I'll do that. And so we'll see how it goes, okay? But for now,
Okay.
I think I could provide the 2 discussion sessions, Tuesdays and Thursdays, and I can address questions after class Monday, Wednesday, Friday, so that you have an opportunity to get questions answered the 5 weekdays, Monday through Friday.
Okay, thank you.